Hello students, welcome to mathematics class. Now in this class, let's start with the new topic of the third unit, that is zero of analytic function and singularities of the analytic function and types of singularities. So first let us discuss the definition of zero of an analytic function. So here a zero of an analytic function f of z is a value of z for which f of z equal to 0. So for example, here suppose that f of z is equal to z plus 3, f of z equal to z plus 3. Now 0 of this function is equal to what? First we need to equate this z plus 3 is equal to 0 and z equal to minus 3. So therefore this z equal to minus 3 is the 0 of that function. Means for the value of z equal to minus 3, the given function is giving the value as 0, hence that z equal to minus 3 is the 0 of the analytic function f of z equal to z plus 3. And then order of 0. If f of z is analytic in a domain D and A is any point in D, f of z is analytic in a domain D and A is any point in the domain D, then by Taylor's theorem f of z can be expressed as f of z equal to summation over n equal to 0 to infinity a n z minus a whole power n. So that is the expression for f of z by using Taylor's theorem, where a n is given by f power n of a divided by n factorial. So here power of f represents the order of differentiation. So if a0, a1, a2 so on up to am minus 1 equal to 0, here a0 equal to what? 0 order derivative, a1 is first order derivative, a2 second order derivative, and so on am minus 1, that is m minus 1th order derivative. But am is not equal to 0, means all the derivatives up to m minus 1 are equal to 0, but the mth order derivative is not equal to 0. That only we have written here, f of a, f dash of a, f double dash of a, so on up to f for m minus 1 of a equal to 0. All the preceding derivatives are 0, but only f power m of a is not equal to 0. Then we can say that f of z has a 0 of order m at z equal to a. So means here while defining the order of 0, we are concentrating on the value of an for which an is 0 and its order can be considered as the order of the derivative. So here all the preceding values of a0, an, a2 so on up to a minus 1 are 0, but only am is not equal to 0. Means if any one of them among these is non-zero, then its previous or that order can be considered as the order of derivative. Suppose here a3 is non-zero and then again a4, a5 are 0, that doesn't matter. That a3 is non-zero and a2, a1, a0 are zeros, then we can consider that 3 as the order of that 0. So therefore here we can consider f of z is equal to am z minus a whole power m. Here actually in this n is equal to 0 to infinity, but here we are considering the first term as am because all the terms up to am minus 1 are equal to 0. Then am plus 1 z minus a whole power m plus 1 and so on up to infinity. Now we can take that z minus a whole power m common, remaining am plus 1 into z minus a, because in this m plus 1 we have taken that m outside, then remaining 1 and so on up to infinity. This is the function of z into z minus a whole power m. So it is about order of 0 and then simple 0. If f of z has a 0 of order 1 at z equal to a, then f of z is said to have a simple 0 at z equal to a. So here order of 0 can be considered as, that is the power of the factor z minus a. If z minus a is having the power equal to 1, then that is simple 0. Here z plus 3 is there. Now here it is a simple 0, because at z equal to minus 3 its value is 0 and its power is 1, right? Suppose if you consider this as z plus 3 whole power 5, and now this z minus 3 is a 0 of order 5, means whatever the power is there, the same power will be considered as the order of 0 for that function. And now singularities of analytic function. So before going to start this singularities of analytic function, so let us recall the definition of analytic function. So analytic function means the function must be differentiable in some domain D, then we can say that the function is analytic in the given domain D, right? So here singularities of analytic function. Singularities means they are the points in the domain D, and at those points the function is behaving some of different kind. So here by the behavior of the function f of z, we are going to define singularities of analytic function. So here let us start the definition. A singularity of an analytic function f of z is the point at which the function is not analytic. Here this is very important. The point at which the function is not analytic means at the point at which the function is not differentiable, at that point, or that point is called as singular point of the analytic function or singularity of analytic function. So therefore if more than one point is there, so they are called as singularities. So the points of the domain at which the function f of z is not analytic, they are called singularities of f of z. So here let us consider the example f of z is equal to 1 divided by z minus a. So here by looking at this, we can say that the function is not defined at z equal to a. If the function itself is not defining, then how it is differentiable, right? So therefore the function is not analytic at z equal to a. Hence z equal to a is the singularity of f of z in the given domain. That is about singularity. Singularity means we are concentrating on the factors of that z in denominator, but while finding the order of 0 of the analytic function, we need to find the value of z such that the value of f of z equal to 0. If denominator becomes 0, the function not defined, right? So therefore while finding the singularity, we are considering the terms in the denominator, but while finding the 0 of the analytic function, we are considering the terms in numerator. And then isolated and non-isolated singularity. Let z equal to a be a singularity of f of z, and if there is no other singularity within a small circle surrounding the point z equal to a. Here a is a singular point, means at that point the function is not analytic. And if you draw a small circle surrounding that point, means by considering z equal to a as the center and radius is very negligible, we need to draw a circle. So after drawing that circle, if there are no singular points in that circle, then that point is called as isolated singularity, otherwise it is non-isolated singularity. So here z equal to a be a singularity of f of z, and if there is no other singularity within a small circle surrounding the point z equal to a, then this point is said to be an isolated singularity. If or otherwise it is called non-isolated singularity, means if there are any other points in the same circle, then that z equal to a cannot be considered as isolated singularity. Isolated means that should be unique in that circle. So for example, here f of z equal to z plus 1 divided by z minus 1 into z plus 2. Now the above function is analytic everywhere except z equal to 1 and z equal to minus 2. Here z minus 1 equal to 0. If you consider like that, then it will give the value as z equal to 1, and here z equal to minus 2. At these 2 points the function is not defining. If the function is not defining, the function is not differentiable. So therefore these are the only singularities of this function, and also there are no other singularities of f of z in the neighborhood of these points. Means if you consider 1.1 or 0.99 or minus 2.1, minus 2.2 or minus 1.99, like that, at those points the function is analytic, means that is differentiable. So therefore this 1 and minus 2 are the isolated singularities of the given function. So this here singularity, isolated and non-isolated singularity. And now analytic and principal part of Lorentz expansion. So we know the Lorentz expansion, which is containing two parts. One is positive powers of z and one is negative powers of z. So here f of z equal to summation over n equal to 0 to infinity a n z minus a whole power n, and summation over summation over n equal to 1 to infinity b n z minus a whole power minus n. Here the expression or the summation n equal to 0 to infinity a n z minus a whole power n is called analytic part of the Lorentz series. The first part is the analytic part, and the second is bn z minus a whole power minus n. So this is called principal part of the Lorentz series. So therefore here first part and second part. So now depending on the principal part, we are going to define types of singularities. One is removable singularity, essential singularity, and pole. Now first, removable singularity. If the principal part of the f of z contains no term, that is bn equal to 0 for all n, means in this expansion, if the principal part is absent, this part is absent only if bn equal to 0. If this constant is equal to 0 for each value of n, then that singularity, means that value of z, is called removable singularity of the function f of z. And then essential singularity. If the principal part of f of z at z equal to a contains infinite number of terms. So here, if this part is having infinite number of terms, then z equal to a is called essential singularity of f of z. So here, for z equal to a to be removable singularity, there should not be no terms in the principal part. But for essential singularity, that part has infinite number of terms. And then pole. The principal part of Lorentz expansion contains a finite number of terms, say m. Then suppose that part is having some finite number of terms, then the singularity z equal to a is called a pole of order m. Means the number of terms in that principal part will decide the order of the pole, such that order of 0 means that is the power of the term in the numerator of the given function, that is called as order of 0. Here number of terms in the principal part, here principal part means it should contain negative powers of z, z minus a whole power minus n, means if the z is present in the denominator, those terms are called as terms of the principal part. Means if f of z is in numerator, then that should be considered as term of the analytic part. If z is in denominator, then that is the term of principal part. So such that, like that, here if the analytic part is having finite number of terms, then that pole is called as, sorry, that point is called as pole of that function, and the number of terms will decide the order of the pole. And a pole of order 1 is called simple pole. So that is the, as simple 0 is there, and similarly here we have simple pole. Here also the order of that pole must be is equal to 1. So these are the some fundamental definitions: the 0 of analytic function, singularities, and then isolated singularity and non-isolated singularity, removable singularity, essential singularity, and pole. And let us discuss the examples in the next video.